Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And in today's topic, we will see the problem solving cases for the module 4, so which is CFD techniques. So in the previous modules, we have seen introduction, so where we have solved the continuity equation in differential form and integral form for both conservative and non-conservative forms. Then we have seen the classification of PDE, which is partial differential equation, where we have solved for elliptic equation, hyperbolic equation, parabolic equation, and we got what is the criteria for the discriminant in this equation. And then we have seen clearly the discretization techniques, explicit and implicit, and we had solved a 1D wave equation and diffusion equation. So in the fourth module, so basically the CFD techniques. So there are different techniques. So we have ADI, alternating direction implicit technique, Crank-Nicholson technique, so Lax-Meinhof technique. So these techniques we have. So in this today's session, we will see how do we solve the ADI technique using explicit and implicit methods, and how do we solve this Crank-Nicholson technique. We will see it clearly. Okay, so here we can see that, as I told you, ADI and Crank. So these are the two popular CFD techniques, so which are used to solve any type of numerical problem. So first, the ADI. So what is ADI we will see, and then how to solve that, what is ADI method and how do we solve that ADI method, we will see clearly. And then we will see what is Crank-Nicholson and how do we solve that, we will see. So before this, we have a concept called predictor and corrector, so that we need to see. So predictor and corrector. So these two things you need to know. So before solving any numerical problem for the CFD techniques, so we should know what do you mean by predictor, what do you mean by corrector. Okay, so by the name itself, when we say it is predictor, so it is predicting. So the name itself, it says explicitly that it is predicting something. Okay, what is that something, we will see. Next, corrector, in the sense it is correcting something. So we have different sort of techniques to initialize the values and run the values. But now, so prediction, what is the accurate way of predicting the initial values such that you end up with the accurate solutions or the exact solutions or nearistic solutions, you can say. So example, so we have one domain, square domain, so where we say this is the flat plate, this is flat plate. So on this flat plate, so there is a flow which is happening over it. So there is a formation of boundary layer, and when we solve this type of problem, so which type of method you use is important, and how accurate it is near to the exact solution. So we have some Blasius solutions, which is floor flat plate, and we have some approximate solutions where it will give you the value of thickness of delta, which is boundary thickness, or u value, so with respect to Reynolds number. So these things are available. Okay, and here we need to see what kind of initial values. So when we take the mesh, so we need to supply So at each and every grid point, so what is the value of velocity? So at each and every point, it will give what is velocity, pressure, temperature, density. So these values has to be supplied at all the points inside the domain. So that is nothing but your initialization. So when you give the initialization, so the internal field will have its own values, and from the boundary, so the solution will start generated from the boundary points. Why? Because let's say this bottom points are our internal points. So the boundary points. So basically, let us take this A, B, C, and D. So A, B, C, D, they are called boundary points. 1, 2, 3, 4. Basically, these are called your internal points. So, what is the difference between A and 1, B and 2, C and 3, D and 4? That we need to know. So, when you take A, B, C, D, they are called boundary points where the values what we supply is very different from the internal points. Okay, so or in internal field. So let's say you have 1, 2, 3, 4. At 1, 2, 3, 4, you can give value of velocity as 0 or 1 meter per second or 2 meter per second or 5 meter. That's your wish. But at A, B, C, D, so if you have no slip wall boundary condition, no slip wall. So when we have this no slip wall boundary condition, so what is the meaning, So the value of velocity at the wall, so U is basically is not equal to 0. Sorry, that is for slip wall. So equal to 0 is for no slip wall. So not equal to 0 is for slip wall. No slip, the meaning of no slip is, so when the flow propagates over a solid surface, the first fluid layer will get contact and attached to the wall because of the friction between or the cohesive nature between the wall or the cohesive and adhesive nature. So basically, it's the adhesive nature and the bondage between the wall, solid wall, and the uh, flow. So the first fluid layer will get stick to it. So when it is sticked, so the value of velocity v is equal to 0. Okay. So the value of velocity v is equal to 0 for the first fluid layer. Okay. So for the second fluid layer, what happens? So I will draw here it in realistic manner. So let us take in terms of axis. This is x-axis. Let's say this is y-axis, and this is our wall. So let us take this example as wall. So here the first layer. So here it has a 0 velocity. So this is one. 0 velocity in the sense we have this. So the fluid which is going over it, it will get stick here. So next layer, so what happens? So at U1 it is 0. U1 in the sense, or let's say V1. V1 in the sense the velocity at the wall. Okay, so we will give the terminology. So let's say U and V. So U is nothing but velocity along x-axis, V is nothing but velocity along y-axis. So this would give us U1. Okay, so U1 is equal to 0. So which is at the first layer. So U2 is not 0. Why? Because it is flowing over the fluid layer 1. So when the fluid layer 1 has high velocity than the U1, so what happens actually? Going to Newton's third law, for every action there is equal and opposite reaction. So the first fluid layer will try to stop the U2 or the second layer. So layer 1, layer 2. So first layer will try to stop layer 2. Okay. So this layer 2 will try to push or pull the layer 1. Okay. So with this mechanism, so what happens, So the U2 velocity is reduced compared to u infinity. So the meaning of u infinity is the free stream velocity or the velocity of the flow or the region where the presence of the geometry is not influenced. The meaning is, so when we have a flat plate, that flat plate presence will not affect that region. So everywhere, so the velocity is u infinity. Everywhere u infinity in the sense you take here 1, 2, 3, 4. Any fluid layer you take, the value of velocity is always u infinity. There is no change. Okay, so that is what we have. So here what happens, so u2 will be very less than u infinity. Why? Because this u2 is getting reduced by u1. Similarly, if you take u3, so it is not equal to 0 and somewhat greater than u2. Why? Because so here u2 has some velocity, u3 has another velocity, some relative velocity compared to u1 it is greater, u2 it is more greater. So on it will start and it will reach a point called u infinity. So till u infinity it will reach. So when you take this point, when you collect, you will get a profile. So this is the boundary layer profile till 0.99 times of u infinity. Okay, from 0 to 0.99 times of u infinity, that distance we call it as delta, which is boundary layer thickness. Okay, this is the physics what we need to capture here in the flat plate. Now, so what happens actually when you take the value of velocity initially at wall is equal to 0, then you'll get realistic solution. When you are not taking it as non-zero for no slip wall boundary condition, or let's say any other condition, so it will give the false solutions. Or proper initialization from at the grid point 1, 2, 3, 4, 5, 6, 7, 8, 9, or let's internal point what I'm talking. So these points is very important. Why? Because the solution will start from the boundary points A, B, C, D. So A, B, C, D to start. So already these are defined, but 1, 2, 3, 4. The initial values we need to guess it. Okay, that is nothing but we are predicting it. Okay, so or guessing it or predicting it. So initially when you guess the initial values, so that is nothing but prediction. Correction is nothing but, so let's say we have equations. What equations we have? We are solving for incompressible flow inviscid problem. That is our agenda. So incompressible inviscid in the sense the continuity equation will be dou u by dou x plus dou v by dou y is equal to 0, 2D. So momentum equation that would be dou u by dou t plus u into dou u by dou x plus p into dou u by dou y is equal to minus 1 by rho dou p by dou x. So this is the second equation. First equation, second equation. And the third equation will be dou v by dou t plus u into dou v by dou x plus p into dou v by dou y is equal to minus 1 by rho dou p by dou y. So this is what we have, third equation. 1, 2, 3. We have three equations. For these three equations, we will supply the initial values. So these three partial differential equations, basically they are converted to the discretized equation. So let's say, example I will write it for the continuity equation, let's say. So we are doing it for forward in time, forward in space scheme. U of I plus 1 minus U of I divided by delta x plus V, sorry, here you have read I comma j because it is 2D. So V of I comma j plus 1 minus V of I comma j divided by delta y equal to 0. So you can compare the equation 1 and let's say this is 4. So what is happening? These two equations. So we have replaced completely the partial differential term in terms of the the linear form. Okay, here you can see there is no product values, or let's say there is nothing partial differential equation, or this is like representing without any derivatives and non-linear terms. So it is simple. So we are converting this whatever equations we have 1, 2, 3 in terms of discretized form. So this is also a continuity equation. So equation 4 is a continuity equation, but it is changed to discretized form. Similarly, equation 5 we will write in discretized form, but it is momentum equation only. Equation 3 also will write in discretized form, but it is pi momentum equation. So this is x momentum equation. This is y momentum equation. X momentum equation, pi momentum equation. Okay. So we have continuity equation, we have x momentum equation, we have y momentum equation. Now what happens actually when you give the predictor? So when you give the initial values, first you will predict what is the velocity, what is the pressure. So you will supply these values in the momentum equation, or let's say you will give initial values of pressure. So when you give the initial values of velocity, not pressure, velocity. So when you give the initial values of velocity, you will get value of pressure. Okay. So again you will get pressure. From that, whatever values of velocity you got, you will get a p value which is guess or predicted. Okay, you will keep aside. So whatever you guessed here, you will substitute in continuity equation, and you verify whether it is equal to 0 or not. If it is not equal to 0, again you have to update the guess. How? So the value of guess, let's say we have v guess, u guess. Okay, so u updated value is u guess plus u dash, the correction. V is equal to v guess plus v dash, the correction. Okay, u dash v dash are called the correctors. Okay, and ug vg they are predictors. Okay, with correction again the same procedure will happen. You have to substitute in momentum equation. There you'll get the guess value of pressure, x pressure, there you'll get the values of pressure from x momentum equation, y momentum equation, and again you will substitute the value of, here you will calculate u velocity, here you will calculate v velocity. Those u and u velocity you will substitute in moment continuity equation again, and you will see whether it is equal to 0. If it is not equal to 0, again you will start. So this looping phenomena will happen. This looping phenomena will happen until we stop somewhere. Where? So the difference, so basically equal to 0 is not at all possible. So you will see such a way that 1e minus 8 or 1e minus 11 or 1e minus 6. So you will keep some criteria to stop the simulation. That is called the convergence criteria. Okay, so this is what the background behind the predictor and the corrector. So why we are predicting corrector? Why? Because when you solve when you want to solve a numerical technique, initially if you don't know anything, you will initially guess the value. Once we guess the value, then we will actually substitute it in the equations, the discretized equations, and we'll verify. After verifying, when convergence is not obtained, again you do the reiteration process. So this is what happens in each and every step. Okay. Now let's see what is ADI, alternating direction implicit scheme. So we'll do it for 2D. Okay. So let's take 2D diffusion equation. So dou T by dou T plus, or you can take as equal to alpha dou square T by dou x square plus dou square T by dou y square. So this is what we have. Okay. So alpha, we'll take it as a constant actually. Okay. So it might come this side or this side. There's no problem. Now let us solve this equation. So how do we? By ADI technique. So by ADI technique, by ADI CFD technique, let us solve this 2D diffusion equation. So these are interest. So we need to solve 2D ADI diffusion equation using ADI technique. Okay. So that is what we are seeing now. So ultimately, every time, so the time derivative term will have same, which is u of I comma j to the power of n plus 1 minus u of I comma j to the power of n divided by delta t. Okay, which is equal to alpha into, we have t of I plus 1 comma j minus 2 t of I comma j plus 2 t of I minus 1 comma j divided by delta x square plus alpha into t of I comma j plus 1 minus 2t I comma j plus t of I comma j minus 1 divided by delta y square. So compare these two terms. What do we have? So we have the terms here for x, terms here by now. So the ADI starts here. So this is a generalized expression where we have seen with respect to explicit method, if we have n for all the terms. Now if we have n plus 1 and n, so it will be the combination of explicit and implicit. Okay. So here ADI, the ADI technique in the sense within a time step. So ADI will divide the time step into two zones. One will be n to n plus half. Okay. So one is in between n and n plus half. So other one is from n plus half to n plus 1. Okay. So these are the two zones. So one will be n to n plus half, other one is n plus half to n plus 1. So whatever the equation we have here, the bottom, this equation is written in these two terminologies. One is between n and n plus half, other one is n plus half to n plus 1. So in these two terminologies, we will write those equations. We will write this equation and we solve. So by writing this, what is happening? We are basically dividing the time step into two halves. In the two time steps, one direction, let's say x direction, will have explicit. So the explicit technique will act as a predictor, and next axis, y axis, it will act as corrector, which is implicit. Okay. So alternating direction. So alternating direction in the sense, for first time step, you have x direction explicit, y direction implicit. So next step, the reverse trend will happen, where x will be implicit and y will be explicit. Okay. So this is how we solve the diffusion equation, 2D diffusion equation using ADI method. Okay. So we'll see here the first step. So which is between n to n plus half. So let us write the equation here. So then u of I comma j to the power of n plus half minus u of I comma n divided by, here you cannot write delta t by 2 you have to write, is equal to alpha into, so u of I plus 1 comma j. So we thought this one as explicit. This will be power n minus 2u, sorry, this is t. Okay. So here this will be to u of I comma j plus u of I minus 1 comma j. Powers will be n divided by delta x square. So this term is what? This is explicit plus alpha into next here v of I comma j plus 1. Here what is the power? N plus half. This is implicit minus 2u of 2 v of I comma j 2 u of I comma j to the power of n plus u of I comma j minus 1 to the power of n divided by plus half n plus half divided by delta y square. So here this one is coming under implicit. So x axis term is coming under explicit, y axis term it is coming under explicit, and this is implicit. Okay. Now here it is what happening. So whatever the values power we have n, those will act as the predictors. Okay. So whatever the values we have n plus half, okay, they are acting as correctors. Okay. So therefore what is happening? For a time step, instead of going fully implicit, partial implicit you are going. Okay. So this is what we have. So first is predictor, next one will be corrector. So the trend will reverse when you go for next step. What is the next step? Between n plus 1 and n plus half. So in these two. Okay. So what happens? U of I comma j to the power of n plus 1 minus u of I comma j to the power of n plus half. So this value will come from the first equation or first step divided by delta t by 2, which is equal to alpha into. So now here x what happens? X will be the character. So this will go to implicit. N plus 1 minus 2u of I comma j to the power of n plus 1 plus u of I minus 1 comma j to the power of n plus 1 divided by delta x square plus alpha into u of I plus 1 u of I comma j plus 1 to the power of n plus half minus 2u of I comma j to the power of n plus half plus u of I comma j minus 1 to the power of n plus half divided by delta y square. So this is the next step. So this is how we solve a 2D diffusion equation for the ADI method. So now what is happening actually when you take this ADI method? The ADI method is basically an alternating direction implicit scheme where it is solving a full form of equation, diffusion equation you can take in two steps. One step we have partial implicit, other step we have partial explicit, and then if you take x-axis, that is explicit, y-axis will be implicit. The next step, the trend will get reversed where the x-axis will be implicit, y-axis will be explicit. So in this way, when we assign first initially x as predictor, y will go as corrector, and in the second step where x is coming as the corrector, y will go as predictor. Okay, within one step. So between, actually one step in the sense it is between n and n plus 1. So in between n and n plus 1, we are dividing into 2. Okay, so these two things will make up the stable solution in between n and n plus half. So within one iteration, 2 sub iterations will happen. Okay, so this is what we how or what the technique of the ADI. Next, we are seeing Crank-Nicolson. So basically, Crank-Nicolson is a generalized equation which is second order accurate in space and time. Okay, so we will actually write down the generalized expression. So we'll take again the diffusion equation, so which is 1D. So dou u by dou t minus alpha dou square u by dou x square equal to 0. For this equation, let's apply the Crank-Nicolson technique. So what happens? So this equation we solve such a way that that will be semi-partial or the half explicit, half implicit directly. Okay, for this step, let's see. So u of I comma j to the power of n plus 1 minus u of I comma j to the power of n divided by delta t is equal to, so we have some correction factor. So basically we have half, okay, of u of I plus 1 comma, sorry, here we don't need j. Why? Because it is 1D. So we have I plus 1 minus 2 u of I, so n plus u of I minus 1 to the power of n divided by delta x square plus half of alpha into u of I plus 1 to the power of n plus 1 minus 2 u of I n plus 1 plus u of I minus 1 to the power of n plus 1 divided by delta y square. So we have first half here, second half here. What is happening? So first half is solving explicitly, second half it is solving implicitly. So you have half here, half here. So this is how the Crank-Nicolson technique will solve. So it is called semi-implicit technique. This is half implicit technique, half explicit technique. Okay. So basically this is the difference. So here, what is the difference between ADI? Now we have seen ADI and crank scheme. So when you compare this ADI and crank scheme, what is happening? So here you have two steps. One is between n, this is between n and n plus 1 by 2. So other one n plus 1 by 2. So here what is happening? Here it is straight n to n plus 1 by 2. But in the equation you are doing half explicit plus half implicit. So that is the difference. So here we are not dividing the time step into, so Crank-Nicolson we are going in one way, but here we are taking half explicit, implicit in one go. But in ADI we are not going in that way, so we are doing it in different way. Okay. So with this we have seen the problematic case for the module 4 where we discussed the solving of the diffusion equation using alternating directing implicit technique, and we have seen like how do we solve using Crank-Nicolson technique. Okay, so in the next module we'll discuss further about the other technique to solve the numerical problems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.